kind of a summary sheet of what we've learned so far. So how about equations? Well, the is most important. PV equals nRT. Yeah. And if we need, you know that I will always provide us equations, but it's good to have them kind of handy in one place. Remember, we saw how we can derive an expression for molar mass and for density out of this. So if we need a reminder, molar mass is gram per mole, and then you can derive that mass over N. Sorry that everything's moving so slow today. And then plug in for N to solve for molar mass or solve for density. We also have our Boyle's law, Charles' law, Guy-Lussac law. We can derive those out of this, though, can't we? Okay, what else? And we know the conditions, but what is true at STP? Go. For any gas. So if it reads STP, or if we're given 0 Celsius, 1 ATM, we just need to know that we can apply this if needed. Also, the kinetic molecular theory of gases, that temperature is directly proportional to kinetic energy. That's a good thing to be reminded of. Remember that at a given temperature, there's a variety of speeds or variety of energies. And remember, that's going to be that Maxwell-Boltzmann distribution. So this could be kinetic energy, it could be velocity, and this is number of particles. Just be careful that we don't diagnose the peak to be the highest temperature. All right, we learned how to get velocity, and remember, it's a special kind of average. Square root of 3RT over molar mass. We've looked at problems where we've used molar volume to get us molar mass or to take us from molar mass into density and some other things. So this can be used, of course, as a conversion factor. In a particular diagram, we could use arrows to infer different speeds. We looked at that. That pretty much probably addresses everything that we need for our warm-up questions. So if we just put this to the side, and can you find 7 pages back? So sorry, from the back. If you go to the very back, count that as page 1, second to back, page 2, and so on, or just flip through until you can find these. So the review that we did just now might come in handy. I'd love for us to answer questions 8, 9, and 10 here. 66. Okay. 8. 9, could you put a big old X through 10? And then number 6. So let's see, 5 or 6 minutes. You may talk to each other, of course. Rely on that little yellow sheet if you would like. Move on. I'm going to start with one that you're familiar with or can answer easily.
Or it should be. Yeah, okay, it should be. Yeah, weather, but
You're welcome. Not that you have to. Are you good? Yeah. Okay. Oh, that's excellent.
Find out when we empty. Yeah.
I neglected to let us know that. Maddie, no sweat, because we went over that Friday. 4 gases. The usual form of R, of course, is 0.08206. But because of what we're solving for, this is an exception. If that's what you found as the amount of mold, okay, then okay. So 4 grams divided by
No, that's like.
and that's 0.1. Whenever you're searching for, my reminder to myself is always, if I went more than that, let me get gram per mole. So, and then see which, if that answers it, if doing the rounding. Is that the route you were saying?
I mean, I could have like, changed the words into. Yeah.
Oh, yeah. Sure, for sure.
But that would take.
But that would get you there.
Yeah.
Oftentimes we're trying to identify something and we can find a moment. So that's where my brain has to go. Okay, I'm searching for it. 414. So we could use that. Also, that you may answer it more quickly. You're going the right way.
Yeah, when the smallest one be neon.
Yeah, neon, CO is 2. Yeah.
Oh, wait.
The biggest one. That's not that, right? Yeah.
We'll just give 2 more minutes to these if we can come back if we need.
That's more in the situation.
For the reason.
Yes.
Ricky and Isaac, are you on 8? Okay, and what are you deciding between? All right. Let's go ahead and answer 8. If we're asked about kinetic energy regarding gases, average kinetic energy is temperature. They are all at the same temperature. So they all have the same average kinetic energy. Now, that doesn't mean all the same speed, all the same mass. But if the temperature is the same, all the same kinetic energies. And then if any were higher, that would be the one. Yes. Yes. So temperature plays a role, but so does molar mass. Correct. Yeah. For speed, this is just asking for kinetic energy. The most fundamental, right? 1/2 mv squared. And so if you have 1 mole of them, have different molar masses, if we're saying they have the same kinetic energy, then they can't have the same speed. So, but they can have the same energy. Is that okay? All right, very good. So 8, 9, and 10, DBA 66C. I want to talk through any. Yes, absolutely. Okay. First thing that stands out to me, STB conditions. That may prove handy. Maybe not, but that may prove handy. So I have a 2-liter container and 4 grams of one of these gases at STP. All right, so whenever I'm trying to identify a formula in some way, shape, or form, my brain, Ava, first goes to, can I find the molar mass? Because since I have the formula, I can easily, this is about 64, 28, 44, and so on. I can easily just round and get those. So, 22.414 liter per mole. All right, so I know I have permission to use that. Not that you have to, but my brain thought about doing that. Okay, well, I know my volume, 2 liters. Okay, and it's 22.4. 14 liters. Sorry, my brain. And this gives us 0.1-ish mole. I'm just rounding because I don't have to show work. So I know molar mass is gram per mole. So if this gas is 4 grams in that volume, then my 4 grams divided by 0.1, oh, nice, 40 gram per mole. And I did a bunch of rounding. And when you calculate these, let's see, this is 28 gram per mole roughly. And then, oh, I'm looking at the wrong one. I'm so sorry. This is 56, my fault. 56 and 17. And so this absolutely is the closest. So we're good to go with C. Now, you could have also applied the ideal gas law. So we know the volume, we could rearrange and say, okay, to get my molar mass, I know it's going to be the mass RT over PV. So 4 grams, 0.1. Do I even have to 273.15 over 1 ATM and then 2 liter. Because we could do that as well. Did anyone think of a different route? Ava, did that satisfy? Okay. Any other concerns on these? I don't know if you guys recently have watched Damien walk around the halls of this high school. I bet this is occurring now, and that's not why he's here. Damien, such a celebrity in his mind, because he's in his mind. Celebrity in mind, because he's so, gosh darn, a good thinker, but also his Frisbee skills. Yeah? So, when he walks down the hallway, the little ladies, those accelerated 8th graders, those 9th graders are like, oh. So when he walks down the hallway, the girls are trying to get a touch of him. Or maybe like, throw the Frisbee, let's see you throw the Frisbee. So he's just being held back. That's why he's not here, because the girls are holding him back. So he, of course, when he comes in, starts his day with AP chemistry. So he wants to run here, but he's being held back. So when he gets here, he doesn't quite enter as forcefully because he's being held back. Okay. There is a reason for this. I hope Damien is not offended. I didn't get to ask him ahead of time. I'll tell him that I used him as the example. All right. Okay, if we go back to what we were looking at, the van der Waals equation, and I can detect in my packet that is page 22. All right, so wonderfully, this is quite amazing that a chemist developed a way to get the ideal gas law to apply to real gases. The majority of the time, this suffices. So whenever we plug in values, even for real gases, we'll get very close to the pressure calculated that we would measure in reality. Same with temperature. We'll calculate very, very close using this to what we would measure in lab. But the problem comes in when we have low temperature, like room temperature and such, or high pressure, but also a Damien gas, meaning a polar molecule, yeah, that's going to stick to other polar molecules. So for example, right, if we have water vapor, well, these are pulling on each other. So the pressure of a real gas is less than what the ideal gas law calculates for us. Because these particles are attracting. We know that. Remember with the ideal gas law, kinetic molecular theory, we say we're going to ignore that particle attraction. The kinetic energy is so great, we can ignore that. Not really. So that is why this factor. So because of particle attraction of real gases for each other, okay, so if we want to think of Damien dashing, has frisbee in his hand, calculator in this hand, of course, periodic table in his pocket, and then the little ladies pulling on him, yeah? So when he enters the room, he won't have the forcefulness that he would if the girls weren't pulling on him. So the pressure that we calculate, we actually, because real gases have a lower pressure, if we use the ideal gas law, because this is what we would measure, so to be ideal, we need to add this term, okay? So because of the particle attraction, the gas pressure is lowered when it collides with the walls of the container. Okay, so this would be the pressure that we would measure in lab. And knowing, okay, this is going to be lower because of the traction. So to get this to cooperate with the ideal gas law, we need to add to the pressure because real gases will have lower pressure than if they were ideal. Okay, now, what is this term then? So this term is N divided by V squared. How many do we have? And then what space are they occupying? The more we have, so if there's just one young lady pulling on Damien versus 50, right? So the more that are pulling, the lower the pressure that'll be. But we also take into account A, which are constants that have been developed according to your material. Okay, Isaac, choose one here that has a large A value. Yep, and which has a small in relationship to that. Excellent. Helium, monoatomic, small atom. Ammonia. We'll remind ourselves of this. That lone pair plus electronegative, this is a polar molecule. So these attract each other much more than helium to helium. So this accounts for that. So we're going to have to add a greater value because ammonia has a greater ability to hold back the particles from colliding. Okay. The volume. So this volume is the volume of the container. Yeah. And we say, ideal gases, we're going to ignore volume, right? There's no particle volume. Well, that's okay at high temperatures and low pressures, but not those conditions. At a large volume, we can ignore particle volume. But as soon as we start to get a low volume, which we would have with high pressure, then the particles make up a greater volume of a smaller volume than they do a large volume. I hope that makes sense. So the volume that we measure is not really the volume. So this accounts for the number of particles that are there and their relative size. Okay, so the two main violations that real gases break, according to the kinetic molecular theory of gases, is particle attraction and then particle volume. So these correct for that. So if we have a real gas, this is the version that we're applying. But we would only apply this if you were given those directions. On the next page, I worked out an example for us. So unless you're told to apply the van der Waals equation, do ideal gas law all day long. Okay, so there's an example for us. This asks us to find pressure according to just the ideal gas law. But we understand that if it's a real gas, it's going to have a smaller pressure because of the pool of other molecules. And that's what we're shown. Okay. All right. If fusion. So if we just turn to the page after root mean square velocity. All right. So remember, we talked about effusion being escape of a gas out a narrow hole in its container. So sorry, the copier did not do a good job with page numbers. So if we would have two boxes with chopped samples of gas, oh, it's a little fuzzy. I'm so sorry. And then if we would remove that separator, well, we know gas being gas, it's going, these aren't in your pocket. We know there's going to be an equal distribution because of the way the gas particles move. It automatically does that, right, on its own. But instead of removing the barrier, what if we just put a small hole in it? Well, we know how gas particles are moving. And so as long as this hole is big enough, the likelihood that one of these gas particles will find the hole is great. And then you'll have escape. So the difference of diffusion and then effusion. We can really control the speed or the rate at which the gas moves by the size of the hole. So a narrower hole, there's reduced probability that the gases are going to find it. Please, we don't want to think like, oh, there's a hole. All of the gases want to get out. No, they just do because of their behavior. Okay. Well, a chemist by the name of Graham discovered a relationship that we can apply called Graham's law of effusion. Don't have to remember that that's the actual name. It is the rate of effusion of gas 1, whatever that is determined to be, divided by the rate of effusion of gas 2 is equal to the square root of the molar mass of gas 2 divided by the square root of the molar mass of gas 1. Do we see a bit of a similarity? Speed is equal to, square root of 3RT over molar mass. The relationship is inverse, yes? Yes. Sorry, I had to think about that for just 1 second to make sure I was using the correct terminology. So whatever you're determining to be gas one, that will be your denominator. And then vice versa, because it's really, relying on the relationship of speed and then the molar mass of that gas. All right. Let's see. How are we feeling, Critton? Do you think we need like a problem that would probably like be a hardness of 2 first? No, probably 1.5 at a scale of 1 to 10. And then this is probably a 3.5. Do we start with the 1.5 or just go right to the 3.5? I think so too. So example 2. Please read. Okay. Do you want to just see where your problem solving goes and we'll compare? Does milliliter per minute make sense to be an expression of rate of effusion? Wonderful. Concerns? If we're ever employing an equation, I don't think that I went through this with us. If we're ever employing an equation like this, we need to write the equation, the numbers somehow in the equation, and then your final answer. I love to see as much work as you possibly want to show me, but we need minimally to show the equation, the numbers somehow in the equation, and then the final answer. Questions? Yes. Okay. No worries at all. Knowing I was solving for molar mass, I chose to put the rate of effusion of methane as my gas 1. Because then I know I'm positioning myself to solve for something in the numerator. Silly, but I know I could possibly make a misstep if I'm solving for something in the denominator. That's all. Did you do that? Did you put methane over the unknown or unknown over methane? Sure. And then do you have molar mass of methane over? Perfect. Perfect. And then when you plugged in 24, did you get this first? And you'd have it reverse, of course.
Yeah, so I ended up just multiplying both sides by the square root of gas 6. And so square root of whole mass of gas 6 is equal to that's what I did.
Phenomenal. Very good. So good to catch your own error. Very good. That is our unit. That is our unit. Tomorrow, we know we're doing part 2 of the redox. So again, just be mindful of clothing choice. How wonderful. We didn't have any stains last time that I know of. So we'll do unknown work, but we'll tackle another kind of review question to get us all ready. So the goal is Thursday, we're showing mastery of this material.